Hello, my name is Samuel Schleifer, and this is my Physics 2212 Lab 2 regarding the magnetic field of a bar magnet. Little introduction to this lab. The purpose was to experimentally determine how the magnetic field of a bar magnet depends on distance, compare measured results to theoretical predictions for both on-axis and off-axis magnetic dipole fields. So the topics covered throughout this lab are just those, the on-axis and the off-axis magnetic fields. Some fundamental principles behind this lab. First and foremost, we have the Biot-Savart law, which is just the magnetic field equals a constant, sometimes referred to as Km. Here it's written as mu naught divided by 4 pi times the cross product of the charge of the whatever particle is in question times its velocity times r hat divided by the magnitude of r hat squared. Second fundamental principle throughout this lab is just the magnetic field of a dipole. So the magnitude of the magnetic field is mu naught times 2 times the dipole moments divided by 4 pi times the magnitude of r cubed. And then distance dependence is a big one here. So the magnitude of field B equals KRN, and then using some natural logs, you can get natural log of BX equals natural log of K plus N times the natural log of R hat, magnitude of R. So experimental procedure. First, we oriented our device so the magnetometer aligns with Earth's magnetic field. Next, we located the magnetometer chip on the device, which in this instance was our phone. And then 3, we measured the distance between the magnetometer and bar magnet for on and off axis measurements. So data analyst, you could see we got a bunch of different measurements. On an Excel sheet, we plotted average R, average BX, and then on the right, you can see the natural log of BX versus the natural log of R, making a linear equation, and that coefficient of x in that linear equation is going to what later becomes our n back in, I can't go back a slide, but back in the distance dependence formula. Magnitude of b equals k times r to the n. So yeah, these are the calculations. Magnitude of b bar equals k times r to the n. We're able to get n through the slope on the previous slide, which is around negative 2.1893. Then, passing some stuff around, we get magnitude of b is also equal to mu naught times 2 times the dipole moment divided by 4 pi r cubed, which I talked about earlier. And then, moving some stuff around, we're able to get the dipole moment equals around 2.956 newtons times meters per Tesla. This is my glow script code. So on the left side, you see the function for the magnetic field. Underneath that is observation locations, and then underneath that is just the code to draw the 2 arrows in the output. On the right side, you just see a bunch of the equations used to find R perp, and then to find the D value for distance. So this was the glow script output. On the right side, you see the actual output. On the left, you see the values for b-axis 1, b-axis 2, and then b perp is the same at all 4 locations, so I just wrote it as 1. And then we get big D, which is the distance value, around 0.262337 meters. And using that, we can calculate the magnitude of B at 45 degrees, which is around 2.58908 e to the negative 5th Tesla. So a little discussion about magnetic fields. What if you use 2 identical magnets stuck end to end instead of 1? I would expect the result to be multiplied by some unknown constant. This is because the only difference would be the magnitude of the magnetic dipole moment, and the observation locations would remain the same. And then second question, what if you hadn't compensated for magnetic north and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? I'm just going to read, by compensating for magnetic north, the initial x component of the magnetic field was 0. That allowed us to make sure that the only field we were measuring was that being produced by the bar magnet. If we had not compensated for this, the result would be the superposition of the Earth's magnetic field with the field from the bar magnet.